Welcome, everyone. It's my pleasure to have Hinsak with us. He's an assistant professor at the University of Michigan. And he does some really interesting stuff at the intersection of VLSI architectures and low power and high performance wireless communication. And increasingly, he's combining various different tools like machine learning and energy optimizations to build these kind of very cool systems. Before joining University of Michigan, he worked at TI, since then he has won various awards, including the DARPA Young Faculty Award, the NSF Career Award, and so on. With that said, Hinsak, welcome, and the floor is yours.
Okay, so thanks, Shyam, for kind invitation and hosting this talk. I'm actually very excited to have this opportunity to talk about my research, and I hope everyone is safe and well. I have a pretty long title, Machine Learning Centric Energy Optimized Wireless Systems, VLSI Architectures, and Hardware Efficient Algorithms. And my name is Hoon-Seok Kim. I'm an assistant professor at the University of Michigan. So I'd like to start my talk by highlighting the difference between being energy efficient and low power. So being energy efficient and low power are not the same objective, although some may think that they are equivalent, which is not true. So in fact, being energy efficient and low power are often contradicting requirements, and low power systems are typically energy inefficient. So for that, for example, consider this high performance Wi-Fi and low power Bluetooth low energy. Wi-Fi supports up to 300x higher throughput than BLE while consuming 30x higher power than BLE. So the question is, which one is more energy efficient? And as you can probably guess from the numbers, if you calculate the energy per communicated bit, you realize that Wi-Fi is actually 10 times more energy efficient than BLE, although its power consumption is 30x higher. So of course, BLE uses simpler modulation than Wi-Fi, so it consumes less power, but its data rate is sublinearly lower. So this low performance is bad for energy efficiency because the overhead of running local oscillator and PLL in background wastes significant energy when the data rate is lower. And Wi-Fi uses more advanced signal processing schemes such as MIMO, OFDM, and error correction coding. So the analog power consumption is higher due to wide bandwidth and high linearity requirements. But thanks to advanced modulation schemes, it can send more information bits given the unit energy. So overall, it's more energy efficient, much more energy efficient than BLE. So my argument here is that high performance often leads to better energy efficiency, and low power design does not necessarily provide high energy efficiency. So I'm going to present some of my group's recent research projects where we embrace complexity of advanced signal processing and deep learning to save energy. Okay. So in general, achieving high energy efficiency is more important because we want to do more work given limited energy. But we also care about being low power because of several reasons. Some systems must be always running without duty cycling. So in that case, always on operation, of course, needs to be low power. And some systems need to be powered by energy harvesting. Then the average power is constrained by the harvestable power, which sets the low power requirement. And the sometimes thermal and peak current limitations impose additional low power constraints. So because of those reasons, many systems need to be low power and energy efficient. And as I mentioned earlier, they can be contradicting requirements. So designing a system that's low power and energy efficient is a major challenge, and it's the main focus of my research and also today's talk. So my research area covers wireless communication and signal processing algorithms, as well as VLSI circuit designs and system implementation. So I like to talk about three different projects that are cross-layer optimized with machine learning and signal processing to maximize the system level energy efficiency with low power consumption. Okay, so these are the three projects that I like to go through in today's talk. First one is the energy efficient ultra low power wireless transceiver for millimeter scale IoT. And the second is always on millimeter scale intelligent imaging system SoC and system. And the third is deep learning based joint source and channel coding for wireless communication. Okay. So at the University of Michigan, multiple research groups are collaborating together to design millimeter scale sensing and computing platforms. And we have demonstrated various versions of millimeter scale Michigan micro mode or M-cubed systems by stacking multiple custom design chipsets. And they are complete standalone systems with energy harvesting IC, processor, battery, and wireless transceiver, and antenna. And for the first topic that I'm gonna discuss, I like to talk about RF communication system for M-cubed. And the research question that I like to answer is, given millimeter scale form factor, what's the energy optimal wireless communication system for relatively long non-line of sight operation? And to answer the question, we have designed a new RF system from clean slate by investigating various aspects, including the antenna topology, carrier frequency, modulation coding scheme, and also other system parameters. Okay. So our system addresses a few critical challenges related to millimeter scale form factor. And the first challenge is the limited system dimension, of course. And since the overall system size is very, very small, we don't want to increase the volume by having a crystal. So that's the first challenge. And the extreme size constraint also limits the battery capacity. So the millimeter scale thin film battery, SIMBAT battery we use has only 2 microamp hour capacity, and it also has high internal resistance and this means that it has limited peak current, which is only 30 microamps. And the antenna size is very small, so the 3 by 3 by 2 millimeter antenna, magnetic loop antenna that we designed only gave us 0.002 radiation efficiency for our carrier frequency of 915 megahertz. So existing commercial connectivity solutions are not really applicable to millimeter scale systems, first of all, due to excessive power consumption and the also implicit requirement of using centimeter scale antenna with 50 ohm matching. And they have RF frequency stability requirements. So using a crystal clock reference is unavoidable. So our proposed solution, on the other hand, does not require any crystal, and its power consumption is only 61 microwatt, and it is designed to work together with a millimeter scale antenna. Okay, so for relatively long distance communication with a very poor antenna, the transmitter needs to transmit with relatively high power level at milliwatt level, but the maximum current that we can draw from the thin film battery is limited to only 30 microamp. So we need to solve this mismatch by using a energy buffer capacitor instead of pulling the current directly from the battery. So the transmitter pulls high current from the capacitor for generating relatively high power RF pulses. And after transmitting each pulse, the battery trickle charges the capacitor to its nominal voltage. And at the same time, we have this millimeter scale PV cell, which trickle charges the battery with the harvested energy. Okay. So after RF pulse transmission, there must be a long idle period to trickle charge the energy buffer cap. So the pulse needs to be sparse in time. So to exploit this sparsity, we encode the message using the position of sparse pulses. And for the system, there are 64 possible pulse positions, and we can send up to 6 bits using a single pulse to reduce the energy per information bit. And we call this sparse PPM, pulse position modulation, because there is a mandatory minimum idle time between pulses to charge the energy buffer cap. And this recharging time is much longer than the pulse width itself. Okay. And our system supports a trellis coding for error correction coding with variable rates. So this slide shows an 8 ppm example with rate 1/3 trellis coding. And there are 8 possible pulse positions in this example. And each information bit creates 3 coded bits after trellis coding. And using those 3 coded bits, we select one pulse position. So each information bit now is encoded using a single pulse whose position is selected by from 8 possible pulse positions. And this example shows 2 different bit sequences, 000 and 100, where only one bit is different. But as you can see here, pulse positions are completely different because of the proposed trellis coding. So the system can correct some pulse position errors. Okay. And the design transceiver can change the coding rate from 1/6 to 6. And you can also change other parameters like pulse width and the number of repetitive pulses. And this dynamic modulation parameters are used for link adaptation to improve the energy efficiency depending on the channel condition. And I have a slide to show quantified result on that. Okay. And this shows the overall architecture of our RF transceiver. And for the antenna, we use a 3D magnetic loop antenna printed on PCB. And we use this antenna as an inductor of the power oscillator circuit to generate RF pulses. And this antenna and TX circuit are co-designed to eliminate the need for impedance matching between the circuit and the external antenna. Okay. And this slide shows the power oscillator circuit to generate RF pulses. And it's actually a standard LC tank power oscillator circuit. But the inductor here is actually the 3D magnetic loop antenna itself. And we use an external cap, C1, to form an LC tank for RF pulse generation. And the RF carrier frequency is determined by the inductance of the antenna and the off-chip tuning caps here. So, and it has relatively high energy efficiency, power efficiency of 32% from this power oscillator. And actually, we share the same LC tank power oscillator circuit for the receiver as well. And compared to the TX mode, the only difference is the bias current applied to the power oscillator. And for TX, we use higher bias current to oscillate the circuit. But for the RX, we reduce the bias current so that the circuit does not oscillate, but it's actually close to the oscillation point. So in that setting, the power oscillator can amplify the RX signal when the received signal has the matching frequency component of the circuit. So we call it a Q-enhanced amplifier because it provides significant gain, up to 20 dB gain before LNA. And this diagram shows how we construct the 3x3x3 millimeter stack system, including the antenna shown here. And there are 4 PCB boards, and the middle PCB is the 3D antenna and the RF transceiver chip. And other chips are stacked and mounted on the top PCB. And as you can see, there is no crystal in the system. And we have only 2 energy buffer caps and 1 more cap for the LC power oscillator. This is the C of the LC power oscillator. And this is the upside down view. The battery and PV cells for solar energy harvesting are stacked on the other side of the system. And we need to do that because it needs to be exposed to ambient light for energy harvesting. And we apply clear epoxy on this side, and we apply black epoxy on the other side. And the reason we use black epoxy is to protect low power circuits that are very sensitive to light. Okay, so we use a sparse pulse position modulation, which relies on accurate timing, but our RF transceiver is designed without a crystal or PLL. So using a power oscillator allows very simple transceiver architecture with low power consumption. But the problem is that the transceiver now has a very significant carrier frequency offset and the sampling frequency offset, right? So we address this CFO and SFO issue by applying signal processing in the gateway to mitigate CFO and SFO. And we actually design a real-time gateway using USRP X310 and implementing the algorithm on the FPGA. Okay, so let me just quickly go through the proposed protocol. So the millimeter scale sensor node first initiates the communication by sending a pulse train with constant interval. And those pulses have carrier frequency offset and the sampling frequency offset. And the gateway algorithm on the FPGA continuously look for a pulse train, which is preamble, and it estimates the carrier frequency offset and the sampling frequency offset to synchronize the timing as well as the carrier frequency between the sensor and the gateway. And then the node switches to the RX mode with a constant delay, which is measured by its local timer. And the gateway sends the return packet at the right time and right carrier frequency after correcting CFO and SFO. So the receive process on the sensor node does not require any synchronization process because the gateway sends the synchronized message after CFO and SFO correction. Okay. And for dynamic link adaptation, the message from the gateway contains the optimum mode selection for the sensor node given channel condition. So the optimal mode parameters, including the pulse width and the coding rate to maximize the energy efficiency or data rate given the channel condition. And this is the link adaptation result. Left plot is the energy per information bit, lower the better. And the x-axis is the distance, and the target data rate is 10 kilobits per second. And the transceiver supports multiple parameters like coding rate, number of pulse repetition, and the pulse width. And by selecting the right mode combination, the system can optimize the energy per information bit. And as you can see here, the system can achieve less than 1 nanojoule per bit for short distance communication, which means that we can achieve better energy efficiency than Wi-Fi and BLE. And at the same time, our transmitter only consumes 61 microwatt, which is 100x lower than the commercial BLE. Okay, so this picture shows the integrated stack system for demo, and the size is 3x3x3 millimeter, and there are some related publications. the system consists of several custom designed ultra low power ICs. And here is the RF transceiver chip, which is fabricated in TSMC 180 nanometer. And the antenna PCB is shown here. And we have other chips that are stacked on top of each other. And here is the field trial picture. We conducted both indoor and outdoor field trials. And for the setting shown here, we achieved 64 meter for outdoor and 47 meter for indoor. And we also validated communication through concrete wall of a classroom for indoor to outdoor communication, which was about 20 meter. And actually recently we made a 300 meter communication version, long distance communication with slightly bigger antenna, but I didn't include it because it's pre-publication material. Okay, so this is the summary of the first topic. We demonstrated an ultra low power and energy efficient wireless communication solution for millimeter scale sensor node, and to reduce the complexity and power, antenna and power oscillator circuits are co-designed without a crystal. And we demonstrated longer than 50 meter distance with 3 by 3 by 3 millimeter prototype. Okay.
Very cool work on M3. It's a very well-known system. The question I have is, how do I think about the PPM and how much higher data, how much higher can you push the data rates over here? Because if you're eliminating an oscillator, you're limiting the kind of modulations you can do. So can you tell me a little, can you just talk a little bit more about like, what would be the limits in terms of data rate you can achieve?
Right. So the maximum rate that we can show is 250 kilobits per second. So for that, we use the shortest pulse width, which is 1 microsecond. And the biggest concern is the sampling frequency offset and carrier frequency offset. So the gateway needs pretty high SNR to correctly estimate the CFO and SFO, so that 250 kbits per second is limited to very short distance, maybe a meter or two. But we can scale the throughput from 250K to a few hundred bits per second, not K, but a few hundred bits per second. I'll move to the next topic, which is the always-on millimeter scale intelligent imaging SoC and system. And in this project, our goal is to demonstrate a millimeter scale intelligent imager system. And the total system dimension is 10 by 10 by 5 millimeter, including the lens here. And the system includes custom imager sensor chip and RF transceiver that I just explained, and also flash memory to store images. And the key component in this system is the new image signal processing or ISP chip for deep neural network processing and image compression. And those are all custom design chips. And in this talk, I'm going to focus on the new ISP processor. And a picture on this left is the system before encapsulation, and this is the after encapsulation. And we have a testing setup shown here to test the system after encapsulation. And debugging is very painful, but this kind of system helps to debug the system. Okay, so I'm going to focus on the new ISP processor chip for ultra low power image signal processing for millimeter scale system. And this new ISP consumes only 170 microwatt when it's active for deep neural network operation. And the ISP chip is designed for various security and safety applications where you need a miniaturized imaging system. And it's collaboration with Dennis Sylvester and David Blau, and there are related publications. And designing an ultra low power ISP processor for a millimeter scale imaging system is of course very challenging because battery size is very limited with limited capacity, while the application inherently requires large amount of data to be stored and wirelessly transferred. And the standby power leakage is one of the major concerns because the system needs to be needs to have large amount of on-chip SRAM, and it needs to be always on for a security application. So the leakage from the memory is actually quite substantial if you don't optimize it. Okay, so to address those challenges, we exploit the sparsity of information to save energy. And to exploit this information sparsity, we apply signal processing and machine learning to the SoC. And the first sparsity we like to exploit is the temporal sparsity. So if you look at images captured by the security system, the images are mostly the same background, and only a few images contain an event of interest, which happens very rarely or sparsely in time. And even the images containing some events of interest, only a small portion of the image is relevant. And in this example, we mostly care about the face identity of this person in this scene. So the information is sparse in spatial domain as well. So this temporal and spatial sparsity provides us opportunities to optimize the energy consumption at the system level. So let's first consider a naive system that stores images in the flash and wirelessly transmit images for the scene analysis in the cloud. So of course, it's a valid system, but it consumes too much energy on wireless communication, which can be mostly removed by making the image system more intelligent. So that's why we added this proposed ISP processor to give intelligence at the sensor to save energy. So this machine learning enabled ISP processor has capability to detect interesting images that are temporally and spatially sparse. And to detect important images, it performs hierarchical event recognition, and it only compresses the useful part of images that contain meaningful information. And this is a diagram, shows the overall SoC architecture. And this SoC was fabricated in TSMC 40 nanometer technology. And the area is 5.6 by 4.8. So I'm going to explain each component in this SoC. So it has imager interface to take images from the sensor. And it first runs change detection to store change detected macro blocks using JPEG compression. And the system never stores uncompressed raw images. And when system performs signal processing or deep neural network on the captured JPEG images, it performs on-the-fly JPEG decompression when you read out the image from the memory so that you can run deep neural network or signal processing on the raw pixels. And it has an ultra low power neural network engine, which can accelerate heterogeneous deep neural network algorithms. And it's a general purpose DNN engine, which can be programmed for CNNs and fully connected layers and so on. And it has about 655 kilobytes of on-chip custom designed ultra low leakage SRAM for DNN weights, which are compressed only using 2 bits per weight on average after compression. So with compression, we can store up to 1.2 million compressed weights on this on-chip memory. And it also contains H.264 engine to further compress the image. And this H.264 provides higher compression than simpler JPEG. And we actually customize this codec so that it can compress an image with non-rectangular region of interest, which is not supported in the standard H.264 codec. And ISP also has a general purpose Cortex M0 processor for orchestrating all the blocks on this SoC. Okay, so now I'm gonna walk you through an example scenario, which is intruder detection. And this ISP is fully programmable for other applications, but this example is the main scenario that I'm going to use to analyze the performance and the energy of the system. So the first step is the person detection, and this companion image chip has a built-in motion detection mechanism, and this chip sends a subsampled 32 by 20 pixel image to ISP for person detection when motion is detected. And this neural engine performs deep neural network-based person detection on this 32 by 20 pixel image to determine whether it contains a person or not. And if it detects a person, then ISP requests a full VGA frame, 640 by 480, from the imager. And now the ISP analyzes the incoming VGA image and it compares to the reference image to perform on the fly change detection as well as the JPEG compression. And we only store change detected region using on the fly JPEG compression. And the system never stores uncompressed raw images. And when we perform deep neural network on the change detected region, it needs to do on-the-fly JPEG decompression to temporarily convert it back to the raw pixels. And then this neural engine runs DNN-based face detection on the change detected region. And it uses sliding window-based approach to detect a face in the change detected region. And after that, we also do DNN-based face recognition this time, which is only performed on the face. And if the DNN classifies that this is an intruder, then the change detected region are H.264 compressed, and it is stored in the off-chip flash memory. And then the image is later radio transmitted wirelessly. So this shows the flow chart of the hierarchical image recognition of the intruder detection scenario. And each step is conditionally executed only when the previous step satisfies the preceding condition. And this bar graph is the energy for each functional step for a full VGA image processing. And actually, most of the time, the system stops here when the person is not detected in the first step. And this first step only consumes 14 microwatt if the person detection is triggered every second. And following steps, face detection and recognition consumes more energy, but of course they occur relatively rarely. So they are not really the main energy contributor for the system. And the H.264 only compresses the change detected region. So the amount of compressed data after H.264 is actually very small. That's why the radio transmission energy is actually smaller than the internal signal processing energy. Okay, so now I'm gonna provide some more details for key techniques.
I have a question. So what is exactly being transmitted? Is it the compressed video or just the changes of what the relevant person is? What's being transmitted?
So we first do this change detection, and this is an intruder as a result of face recognition. And then we only compress this non-rectangular region of interest, which is from change detection. And each macro block is H.264 compressed. And we transmit only that portion.
I see. So this is designed for intrusion detection, where the assumption is that the amount of change is small and rare.
Yeah, exactly.
There would be a different assumption if you're having a wearable device, or
right.
This is basically for intrusion. Okay, cool.
Right. Possible to program this system for other applications, but we are just using this as a demonstrator of the capability. Yeah.
Question?
Sure.
How is energy efficiency done over time? I missed that part. The temporal, like how do you take advantage of the temporal sparsity? Like, do you keep doing the change detection
yeah.
every time frame,
So
or?
we have a companion imager which only triggers when there is motion. So that's the first mechanism to save power to exploit the temporal sparsity. And when there is motion, it only sends 32 by 20 pixel tiny image for person detection. So that's why this step consumes very small power. So if motion is triggered every second, then you will only consume 14 microwatt in the system. And then it consumes more energy for face detection and recognition, but that's only after person is detected.
So the motion detection is a different sensor.
It's a different sensor, yeah.
Okay.
Yeah. The chip I'm describing is the digital image signal processor. And we have a companion imager sensor chip, which is designed by other group, not by my group.
Can I have a quick question?
Sure.
So in this case, you designed this ML algorithm to do face recognition or person detection by looking at changes. So here is another question. Let's say my design is basically I want to design a chip to do compression. What would be the power and just transmit this power compressed MPEG video to the wireless chip? What would be the power consumption, and how does that scale? Also, how does your system scale with the resolution of your video if I'm doing HD versus VGA versus all those things?
Yeah, so first of all, this particular chip doesn't have any general codec. What it has is the H.264 intra mode, which can compress an image. And if you like to compress video, then one possible solution is to use neural network-based video compression algorithm. Actually, we have a paper on that. So it's possible to compress a video using neural network. So that actually gives you better compression than MPEG or H.264. So you can consider that. And that algorithm, that particular algorithm is scalable because it does, it allows block by block compression. So its energy consumption will be linearly proportional to the number of pixels that you have to deal with. But if you can have sustain that much energy, then that algorithm can run on the system.
And how does the energy consumption of implementing this neural network compared to implementing an MPEG system?
Right. So neural network based one will be easily 10x more complex in terms of number of operations, even more. But the key idea is you spend more energy for compression, but the resulting number of bits will be smaller. And 1 nanojoule, so that's the energy efficiency of wireless communication. So with 1 nanojoule, actually you can do I need to do exact calculation, but if my calculation is correct, you can do 1 million operations. Because
so basically the intuition is that, like, while a neural network based codec would potentially be 10x more complex computationally, the resulting compression would potentially save with the wireless transmission power. So we need to think about system power consumption, which combines both of them, and you might get some wins there. Is basically what you're saying.
Yes. Yeah.
Okay. Cool.
And that's possible if you have an extremely efficient neural network engine. That's the key. If you do it in the regular Cortex M0, you're not going to win.
Yeah.
Yeah. So the compression techniques, mostly talked about this already. So we do JPEG and neural network weight compression to pack more weights, 2 bit per weight on average. And then we do H.264. So compressing weight is very important because always on application needs always on memory. So the leakage actually could be comparable to the active power consumption for ultra low power system. And to reduce the leakage, you need to reduce the memory size by compressing contents. And we also designed a custom SRAM with 0.3 volt for the bit cell to cut down the leakage by 2.4x additional. So the total leakage reduction is 12x. So the standby power is now 12, but it was 150 without this optimization. And 150 is actually close to 170, which is our active power consumption. And for change detection, one naive approach would be storing raw pixels and then doing pixel by pixel comparison for macro block-wise change detection, but that incurs additional overhead to read raw pixels from the memory, and the amount of storage that you need to store raw pixels is also quite large. So what we did is we did a new sparse census transform-based encoding of each macro block. And by doing that encoding, we can reduce the image size from 3 kilobit per macro block to 64 bit. And for change detection, what we do is we basically calculate the Hamming distance between encoded bits, 64 bit per macro block, between the reference frame and the new frame. And if the Hamming distance is larger than the threshold, then we detect the change from the macro block, and that's how we reduce the power on the change detection. And when you store a new image, we only store the change detected macro blocks, which is like this. And for the final image compression, we use a customized H.264 to handle this non-rectangular region of interest. So that's not supported in the regular codec. And so that's what we do. And in the final, for the final output, we need to stitch the reference image and the change detected image like this. And this is what we get at the central node after getting the compressed image for the change detected block. So if you combine the change detection with H.264, you can actually get almost 200x compression compared to storing the entire image. Okay, so this is the neural engine that we fabricated, and there are 512 units of 8-bit multiplication and accumulation units. And weight decompressor here decompresses weights on the fly and feed weights into the MAC array. And we have a dedicated RISC processor, custom design processor, and it controls the MAC array for convolution and sparse or dense fully connected layer calculations. And this ultra low power neural network engine can achieve 1.5 teraops per watt peak performance with 0.6 volt operation, including the overhead of weight decompression and memory accesses from custom ultra low leakage SRAMs. So it's actually more than 200x energy efficient than the mobile processors and mobile GPUs, which has only maybe 1 gigaflops per watt, not tera, 1 gigaflops per watt, or even lower.
Is this processor like actually produced? Like,
yes, yeah, we designed from RTL and then fabricated, and it's integrated part of this chip.
Is it, well, I guess, is the cost worth it? Like, for, I'm guessing it was a small batch.
Oh, if you're talking about the commercial value, then yeah, of course you need millions or 100 millions of chips to make a product. But this is research project to show that show the benefit of having such an energy efficient neural network engine.
I see. So what's the price range for a chip like this?
To fabricate this chip, you mean?
Yeah.
1 millimeter sphere would cost you $10,000. So this is 12 millimeter sphere.
I see.
But we have a university shuttle program between TSMC and University of Michigan. So this was free.
Oh, wow.
Yeah, but the design time is the main cost, right? Several students, PhD students, worked on this project for longer than a year. So that's the cost.
Got it. Yeah. Thanks.
So I have another question. So you mentioned earlier that you basically designed this for face detection or human detection thing, right? Mm-hmm. How programmable is it? Like, what else can you change, and what are the constraints of what you can change in terms of, can you detect a squirrel or can you detect a cat? Like, how programmable is it, and what are the limits of it? Yeah.
So this is basically a neural engine. So you can just program it for convolution, fully connected layer, max pooling, ReLU. So you can specify input channel, number of input channels and output channels. So it's fully programmable. The only limitation is the size of the memory, right? So you can only fit relatively small networks. But other than that, you don't have any restrictions as long as you use a conventional CNN or fully connected layers.
So for a system like this, like how he's saying detecting a squirrel, if it's out in the open, how do you still like, can it still do the motion detection?
Yeah, but it will trigger by any motion. That's one disadvantage.
Okay.
But for squirrel detection, yeah, of course, you can design a neural network and train it with squirrel images.
Oh no, I meant in terms of the energy savings. Like if, yeah.
It might consume significant power if it is triggered continuously by some motion.
I see. Okay.
Yeah. So this is the ISA. We have CISC and RISC instructions. So we can do convolution. Yeah, I basically covered this. And this is the neural network performance for person detection, face detection, and face recognition. We get mostly above 90% for face recognition and 95% for face detection and so on. And we trained it with the labeled face in the wild data set, which is a common data set for face detection and recognition. So the chip, this is chip summary. It was fabricated in 40 nanometer technology. This is the size. And for ultra low power operation, actually, we need to run it at a very low clock frequency, 150 kilohertz. And with that frequency, it only consumes 170 microwatt for active neural network processing. But even with that low clock frequency of 150, we can do 5 frames per second for person detection. The throughput for face detection and recognition is slower, but they are less frequently triggered. And the reason why we can do this much throughput is because we have 512 multipliers on this neural engine. And the area is actually dominated by the memory. So the whole thing here, except for this center piece, is the memory surrounding this other logic. So it's a memory dominated design.
Do you have a paper on this already?
Yes, we do have a paper. So I'll send out this slide, and you can find the papers. There are 2 papers on this chip. So we can do pretty high compression because we combine the change detection and H.264. So 100x or even higher compression rate is possible. And the standby power consumption is quite low for person detection. Not standby, the 1 frame per second power consumption for person detection is pretty low. Okay, so this is the summary. So we demonstrated an energy efficient system by embracing the complexity of signal processing and deep neural network computation, and 200x compression and 16x energy saving by transmitting only useful information in compressed form, and additional 10x energy saving by performing hierarchical image recognition to exploit the temporal sparsity. Okay, so the final topic, which is shorter, is the deep learning-based joint source and channel coding for wireless communication. It's a different topic, but I thought this is somewhat related. And so according to Shannon's theorem, source and channel coding can be designed separately without loss of optimality. And as you know, most practical systems adapt separate source and channel coding. So for example, image is first compressed using image compression codec, such as JPEG or BPG, and then people apply separate error correction coding, such as LDPC or POLA. And then separate modulation such as OFDM and QAM for the bit sequence. And this separate source and channel coding is very popular and very practical, but it is suboptimal when the message length is finite. And joint source and channel coding, if you do these jointly, it can be optimal, but it was considered practically infeasible because of technical difficulties to find a write scheme that outperforms this conventional separate scheme. But as deep learning becomes more powerful, people have started to design joint source and channel coding, or JSCC, using deep neural network. And this slide shows a typical DNN-based JSCC structure, and it usually includes an encoder, and the encoder maps the image input to complex value samples Y, and then decoder recovers the image from the baseband received signal Y hat. And the channel is not trainable, of course, but it is differentiable for backpropagation so that the system can be trained in an end-to-end fashion for the encoder and decoder pair. Okay. So prior work on JSCC shows very promising results, but they are designed for simple AWGN and really flat fading channels without considering the more realistic multipath. So that's our new contribution. In our proposed method, we extend the DNN-based JSCC to multipath fading channels by incorporating OFDM signal processing blocks inside the DNN structure. And the input image is first encoded to complex valued symbols, Y, and then we pass Y and also pilot symbols through IFFT and cyclic prefix, as in conventional OFDM. And the signal goes to a multipath fading channel, and the received signal goes to CP removal and FFT, and then it goes into decoder. So in this proposed scheme, in addition to the information symbol Y, we also transmit the pilot symbol YP to help the decoder to estimate the channel. Okay, so for the decoder design, one naive solution is to train a large CNN with receives Y and YP, and to recreate the estimated image X hat. And this naive approach basically let the decoder network to figure out the channel estimation and equalization and demodulation all implicitly. So therefore, we name it implicit method. And it's important to note that we can train this encoder and decoder network pair end-to-end through this OFDM signal processing blocks and also multipath fading channel, because green blocks shown here are fixed functions, but they are all differentiable. So the multipath channel is also differentiable. So when you train the encoder and decoder pair end-to-end, you can propagate the gradient through those green channel, green blocks and the multipath channel, so that you can train encoder and decoder at the same time. And actually, we can do better than the previous naive model using the expert knowledge in the wireless communication domain. So our proposed method provides more explicit structural guidance to the decoder network. And in our structured decoder network, we use explicit channel estimation and also equalization blocks as shown in this diagram. And we add a residual path in parallel using neural networks to improve the quality of explicit channel estimation and equalization. And those green blocks are fixed non-trainable functions. And we just train the subnet, which are in blue. We call it explicit method because we are using explicit channel estimation and other domain expert knowledge. And again, the gradient can pass through those explicit blocks during the backpropagation so that we can do end-to-end training of the whole JSCC network, including those explicit blocks from OFDM and the channel estimation and equalization. So to quantify the performance of the proposed JSCC, we performed evaluation study on.
So I have a question here. This is really cool that you're trying to basically jointly code the both the domain, both the layers over here.
Yeah.
I'm wondering if you're given, if you have some thoughts on how this is going to be used in practice, because if you look at practical systems, right, like Wi-Fi chip is a chip which does the encoding, it does all the coding, LDPC codes and everything else, convolutional codes and stuff, and you just sets a bit rate, and the video is done at the application layer, whether you're using, it's basically at the very high application layer in between this TCP and all those things.
Yeah.
And the good thing about that design, as we all know, is because it's a layered design, the same Wi-Fi chip can be used for audio, it can be used for data and all those other things.
Yeah.
So how do you think of, like, when you're jointly designing the Wi-Fi chip design or the wireless chip design and the application layer data like video, how do you think of generalizing it across multiple data sources?
Right. So the main theme, I think that's an excellent question. So the main theme that I'm investigating these days is the ML-centric, ML-driven vertical system. So we replace compression using machine learning, and we replace coding using machine learning, and even modulation, demodulation, basically everything could be in machine learning space. Then what you need is pretty much an application processor and a very efficient neural network engine, which can handle various machine learning based tasks. Let it be source compression, or let it be modulation or demodulation, right? So what all you need is the neural network based algorithms, and that can be very efficiently executed on that unified hardware platform. So yeah, evaluation study. So we are comparing three different structures. First one is the conventional naive JSCC, which is the state of the art, and it does not use any explicit OFDM. And then the second is with explicit OFDM. And the third one is the most explicit version with expert knowledge in the channel estimation and equalization. And we use CFAR10 and CELEB A images. And CPP here stands for channel use per pixel. So lower CPP indicates more aggressive image compression, and each column shows different SNR of the frequency selective channel. And the top table is the PSNR quality, and the bottom table is the SSIM image quality. Higher the better. And different rows correspond to different schemes. So this is the most naive one, and then more explicit, and this is the most explicit one using the expert knowledge in the network design. And as you can see, you have significant performance enhancement by incorporating the expert knowledge. Okay, so this is the comparison between explicit JSCC with a traditional scheme using the state-of-the-art image compression codec BPG and capacity achieving LDPC for channel coding. And we use multipath fading channel for CFAR10 image transmission, and the compression is 0.21 channel use per pixel. So basically we convey 5 pixels using one complex valued sample. And so it corresponds to high compression rate, and we sweep SNR x-axis, and the y-axis is the PSNR. And there are two red, and actually this one is the upper bound when we use perfect channel estimation knowledge for the baseline scheme, which combines LDPC and BPG and QEM. And we enumerate different coding rate and modulation order and so on to get the best point for each SNR, but still it's significantly worse than our JSCC. And in JSCC, actually, we estimate the channel without using the perfect channel estimation knowledge. So, and it still outperforms the upper bound of the traditional method. And the gain is about 1.5 dB or 3 dB, depending on which image quality you look at. So in the interest of time, I'm gonna skip this. So the idea here is PAPR, peak to average power reduction, is one of the main problem for the OFDM. What you could do is you can just include this signal clipping as a additional nonlinear layer in the OFDM. And if you train the neural network, actually neural network learns how to deal with this signal clipping. So this is the gain with and without signal clipping model in your neural network. And the PAPR reduction is about 3 dB or even higher. So, so this is the result visualization example of our method tested with CIFAR-10 and SALAP-A. Image transmission over multipath fading channel. For CIFAR-10, the CPP is 0.182 and SALAP-A is 0.111. And SNR is 5 dB, so it's not very good channel, multipath fading channel. And the baseline is BPG plus LDPC. And as you can see here, the image quality is not very good because very high compression and bad SNR. And the bottom row here, so the top is the original and the bottom is our proposed scheme explicit method. And it shows very high quality decoded image when even with this aggressive CPP rate and only 5 dB SNR channel. And these are additional example images from Kodak data set. SNR is same 5 dB in the multipath fading channel. CPP is even lower, 0.078, and original and baseline and proposed ASCC. And the quality difference is mostly noticeable here. So JSCC results maintain high fidelity details compared to the BPG plus LDPC plus OFDM QAM, which is shown in the center. Okay.
Quick clarification, is this image compression plus wireless coding, or is this video compression plus wireless coding?
This just image.
Image, okay.
Yeah, yeah. So we put image into the neural network, and then output is the complex samples.
Yeah.
Yeah. This is the last slide. I'll conclude this talk by highlighting a few takeaway points. So being energy efficient is not equivalent to being low power, and they are often contradicting objectives. And embracing complexity to adapt advanced signal processing and machine learning can lead to more energy efficient systems. And as an example, I presented an intelligent image detection image system. And DNN algorithms can enable new energy efficient IoT systems. It is very computationally demanding, but the energy saving can offset the overhead of increased complexity. And this approach is only feasible because of very efficient VLSI architectures. Without efficient accelerators or processors, DNN computation costs will be too expensive. So to exploit the full benefit of advanced DNN and signal processing, we need very highly efficient VLSI accelerators and processors co-optimized with the hardware efficient algorithms. So with that, I'd like to thank you very much for your attention, and I'd be happy to take additional questions if you have any.
Oh yeah, so I have a question on the last topic. So I wonder, so that is for the image compression, basically image transmission. So does it also applicable to any data, like a random text file, for example? So basically, does the neural networks learn a co-existence of an image as well as the channel, or it only learns the channel to recover the data?
So we have actually tested it with audio, and it works well. But the key part is you need to feed the right input to the neural network. Essentially, you're using convolutional neural net to do coding and modulation. So for the audio, it's better to convert the audio to spectral domain, short time Fourier transform. and then the CNN will handle the audio signal well. And for the text, I think the first layer, you might want to use the network structure that you can usually see in the natural language processing network. So you can combine that kind of front end with the back end that I showed here, right, for the WebGen processing. Then I think it's going to work for the text and other modality as well.
I see. So basically, the neural network actually learns how to adopt basically a combination of the channel as well as the characteristics of the data.
Right, but you need different weights if your source type is different.
I see.
So
Yeah,
I found it really interesting because raise your hands if anyone else has a question. But I found this really interesting because if let's say that the channel is changing over time, because that's what happens in wireless channels, right? Like, so do you have I'm wondering if the next step is basically to use reinforcement learning or something to get feedback back and use that as the information, or is that something you're thinking about as well?
So there could be two approaches. One is to train the neural network for many random realizations of the channel. That's what we did. So the frequency fading channel model, we have a model, but we used random realization of the channel for every backpropagation so that neural network learns the average performance. But if you like to get more higher performance for time varying channel for the particular channel instance, then I think you can do more by getting feedback, the channel information feedback from the receiver, so that the network can adapt to the particular channel model that you see, channel instance that you see.
Yeah. Cool. Thank you so much. This has been like over time. We have been 10 minutes over time. But thank you for taking the time to come and present this really cool stuff to us.
Yeah, thanks for inviting me. I really enjoyed to meet you.